Okay, let's get started. Good morning, everyone. Welcome back. So today we are going to talk about the economic dispatch, the optimization problem. But before going to that part, I think I need to remind you what we are doing in this chapter. So this chapter is about the electricity market and its organization. So, forward market and spot market, they are the two key topics. And the European market and the North American markets are different. So that's why we have two imaginary countries, Bulgaria in Europe, they prefer bilateral trading, and Moldavia, some imaginary country in North America. And I told you, Sylvania, toy, the rabbits. Is there anyone who checked that? No one? Check it. It is very expensive, more than $200. Anyway, so yeah, and the thing is, electricity is not like the general commodity, and that's why this electricity market is different from other markets. So electricity is inextricably linked with physical delivery system. That's why we have different types of spot market. Okay, we will talk about that. Actually, spot market, in Korean, that is called 현물 시장. So spot market is very general. So when you go to Yeomridong market, you can buy some banana and give some money. Okay, this kind of spot market. On the spot, the transaction happens. By contrast, in electricity market, they are called managed spot market. So there is an administrator or system operator who organizes and who operates the market, spot market. Okay, and so the managed spot market is run by independent system operator (ISO), and in Korea there is KPX, Korea Power Exchange. Okay, but anyway, before going to this spot market, actually the spot market is we have several terminologies about this spot market or real-time market or balancing market, blah blah blah. So check your textbook about that. But we want to minimize the volume that is traded in the spot market. That's why we have a forward market and future market in advance. Okay, so to reduce the risk, we have forward market and future market. But anyway, thing happens. Sometimes the power generators can break down, or load can suddenly increase or decrease. So that kind of imbalance must be compensated at the spot market, in the managed spot market. Okay, that's the key point. So yeah, forward market, we talk a lot about this, and today we need to talk about this spot market, especially managed spot market. And please remember that in forward market, two types of markets can be possible: the bilateral trading and central trading, depending on Europe or North America. Similarly, yeah. And you may remember this example, Bulgaria Power in Europe. It has 3 units having different marginal cost and different minimum and maximum power generation. So, maximum 500, 250. And you may remember that, so again, our target, today's spot market is June 11th, 2 p.m. for 1 hour. Okay, that is today's managed spot market. And for this 1 hour time period, actually, there are 2 long-term contracts and 3 over-the-counter contracts: January 10, February, April, May, June, blah blah blah. Okay, and time goes on, tick tock, and then you remember that, yeah, this is on the day, June 11th, and before noon. And do you remember what it was? The Boldria Power manager, Fiona. Yeah, Fiona. So this is the position before noon. From long-term contract, this amount, actually, Fiona. So this is the offer, but Fiona wants to buy back because the price this is cheaper than that, and resell it. Okay. So anyway, the net position was 570 megawatt, and the production capacity is 750 megawatt. So yeah, 570, and because 130 megawatt is further available on that day, before noon, she want to sell it further because in the order book she found that 3 bids, and the price, this is higher than this marginal cost. So it would be better to sell it further if somebody can buy it at a higher price. That is this one, these 3. Okay, so she grabbed these 3 offers. But things happened, and she got a phone call, and the unit B has a problem, right? So the maximum capacity is reduced from 200 to 80 megawatt. So that's why, wanted to sell more, 60. So unit 2, 70 plus 60, but the maximum is now 80. So 50 megawatt is in deficit. So bids and offer on the BPEX in the afternoon. So afternoon, but before 2 p.m., she again participated in this electronic trading and grabbed 3 offers that can compensate 50 megawatt, and she is willing to pay this price because she thinks the spot price will be higher than this one. Okay, so it was just before 2 p.m. and today, after we talk about the unit commitment, the optimization problem, we will go to the managed spot market actually and see what happens. Okay, it is an interesting, exciting story, right? Okay. So, by the way, so we also talked about the centralized trading, and this centralized trading can be used for either forward market or in the spot market, but typically spot market is managed by the centralized trading. Okay. And okay, so and on Monday we talked about the day ahead centralized trading. So forward market and spot market, this is real-time market, and at some point the gate closes. That means no further trading is possible but the spot market. So day ahead market is before spot market and is kind of forward market, but this day ahead centralized trading is more like scheduling, solving optimization problem. So, and it is related with unit commitment problem. Okay, so that's optimization problem, and we'll talk about that today. So all of these different types of mechanism is because this electricity market is inextricably related with physical system. So load forecasting is required to determine the amount of required load, and generators submit their bids, and then optimization algorithm runs, and minimum cost schedule is determined, and market price is also determined by the system operator. So this process is similar to spot market, but this is day ahead scheduling, unit commitment. Okay. No, sorry, I need to change my statement. This is optimization problem. Unit commitment is day ahead optimization problem that is run in a centralized way. So anyway, generator has bid, load forecast. So let's talk about this one. The day ahead unit commitment optimization problem is like that. Actually, there is a typo in your slide, so this should be P. Okay. So we have n number of units, the power generators, and T, capital T is the number of time slots per day, like 24 or 96. Okay. So the objective function is the generation cost plus the startup cost, turning on of the generator incurs additional cost. And this UI is the binary variable. 1 means it is on, 0 means it is off. Okay, so this is a scheduling problem. We need to determine whether the unit needs to be turned on or off, and when it is turned on, how much is the generated power. Okay, so this is a mixed integer programming. And the constraint is the total amount of power generation should be equal to the estimated load. L is load. And this optimization problem has several constraints. First one, each unit has minimum and maximum generation capacity, and also ramp rate limits. That means we cannot arbitrarily increase the power generation fast. Okay, so the difference T minus 1 and T is limited by some amount. This is the maximum ramping rate, and also we cannot arbitrarily decrease the output power of the generators. So this difference should be less than something. Okay, and also minimum uptime constraints. This formula looks slightly complicated, but actually what it says is we have a minimum uptime. For example, when minimum uptime is 4 hours, that means when the generator is turned on, it must run at least 4 hours. Okay, and also the minimum downtime constraint here. If this minimum downtime constraint is also, for example, maybe 4 hours, then when it is off, then it should rest for 4 hours. Okay. You may have minimum downtime constraint in your life as well. 8 hours. When I go to sleep, I need to sleep at least for 8 hours, something like that. Of course, it depends on your body condition. Anyway, you see what I'm saying? Okay. And about this one, do you see this formula explains this minimum uptime constraint? So at time t minus 1, the generator is on, and we have some, let's say this is 4 hours, for example. Then when there exists a tau that satisfies this, such that at the time the generator is turned off, then at time t, the generators need to be turned on, keep turned on. Think about it. 1 minute. Actually, time is slotted. Okay, so let's say this is a t minus 1 and this is t. And let's assume that t mean up is 4. So t minus 2, t t minus 3, t minus 4, t minus 5, t minus 6 is on, off. Let's see this kind of this kind of thing is happening. Then what it says, t minus 4 is here, and tau is greater than that. Obviously tau should be less than t anyway. Okay, so tau is either this, that, such that, but we cannot find tau like that. So this need not be 1. So it can be turned off, right? But if this is the case, then t minus 4 tau. We cannot find tau. We cannot find such tau. T minus 4, but greater than. There is no such tau. So it's weird. 1, and there is no such tau. Then it can be turned off. Is it correct? It looks like it should be turned on. T minus 4 to 3. Think about it. I think we need to put the equality sign here. In that case, t can start from here, and because if we have equality sign there, then there exists such tau that satisfy this one. So it must be turned on, and then it runs at least 4 hours. Okay, so think about it, and if you don't agree with me, let me know. So I think we need to put equality sign here. Or I don't know, maybe this tau is not a continuous variable. It's not discrete variable. Maybe this is continuous variable. But I don't know. Yeah, check it. But this constraint says no, we have minimum uptime and minimum downtime in the optimization problem. Okay. So these are example. This is an example. We have 3 generating unit again, minimum and maximum power. It looks like this is different from the previous one. So that is different from this one. Yeah, different problem. Yeah, so we are just talking about unit commitment optimization problem. Yeah, 3 generating units, minimum and maximum, and marginal cost and fixed cost. And we have 3 time period, 1, 2, 3. And this is the estimated load, so we need to meet this demand. And so what you need to do is find the schedule that minimizes the total cost. Okay. Actually, no, the maximum generation is 500, 350, 200, and to meet 550, at least 2 generators should run, right? Yeah. So there are. Yeah. So. Yeah, there are 3 cases because single generator cannot meet it. So at least 2 generators need to turn on, and turning all of this is not actually, yeah, we have 4 candidates, but turning all the generators has higher cost than this one, so that is excluded here. So 3 possibility is turn on P1 and P2, unit 1 and unit 2, or turning on unit 1 and unit 3, turning on unit 2 and unit 3, and then meeting this 550 can be either 450 plus 100, or 500 plus 50, or 350 plus 200. And each generator has its fixed cost and marginal cost. So here, fixed cost 500 and marginal cost 10. So 500 plus, 10 times that plus unit 2, fixed cost 250, and the marginal cost 30 generation, and you can compute the cost. Similarly, case 2 and case 3, you can compute the cost. And you may be curious about, hey, why this is 500 and this is 50? The reason is because anyway, when 2 generators are turned on, now the fixed cost is actually fixed. So we need to increase the most cheapest generator in terms of marginal cost up to the limit, right? So yeah. Then what about, why is it like that? What about we have a minimum generation constraint as well. Okay, so the minimum cost can be achieved in this case, and at that time, okay, next question. Yeah, this is the schedule, and what is the market price? What should be the market price? The answer is here. Why is that? The market price for time period 1 is $35. Why is it? 희주 어라 경용 어라 지훈. So we have an optimization problem. We solve it, and we found a way that minimizes the total cost. And the question is that what should be the market clearing price after solving this optimization problem? This question is related with what? Related with SMP. SMP determines from day-ahead scheduling, day-ahead unit commitment, scheduling, and then so why it is $35? Yeah. No, in the centralized scheduling, we have a common price for everybody. So you remember the supply curve and demand curve, and all the generators that can participate in the trading is paid at the same price, and that price is determined from the most inefficient generator, the marginal cost of that generator, right? So profit of producers and the surplus of consumers, you remember that? So that assumes single market clearing price. Okay. So even though different generators have a different marginal cost, all the generators are paid at the same price. Okay? And why is that? Actually, we already talked about that. Why trade all energy at the S&P using the same price, common price? Why not pay the generator what they bid? Actually, what was their bidding? The bidding is here. We do not have bidding information, but just suppose that this is their bidding, okay, or slightly more than that. But they are not paid as they bid. They are paid using the common market price, and the reason is because there are cheaper generators or more expensive generators, and cheaper generators would not want to leave money on the table. What it says is when they think they can make more money, okay, suppose that the generators are paid as they bid. Okay, so the market price, how can I say? Yeah, this is two different concepts. Option one, there is a market price and all the generators are paid with the price. Option two, each generator gets paid as they bid. Okay, so you may think option two is reasonable, but I'm not. I'm arguing that, and actually the answer is option one is better than option two. And the reason is because if option two, what would happen in option two? The cheaper generator would not want to leave money on the table. That means anyway, the generators wants to maximize its profit. Okay, so yeah, this is my marginal cost, and he thinks, but he does not bid using this marginal cost, but increase his bid because this is what I get. Okay. So he tries to estimate this S&P. What should be the S&P? Okay, so I estimate that and I bid. So hopefully, maybe he thinks S&P is here and my bid is here, so I can have this amount of profit if I get paid as I bid. Okay, but what if this is S&P and but he estimated in the wrong way, so he bid here higher than this S&P. Then even though this generator is a cheap, a very efficient one, he cannot get into the market because his bid is more than S&P, right? So he cannot sell his energy. Right? So occasional mistake can happen, so get out of the schedule. Then from societal perspective, there is loss of efficiency, right? And that also increase uncertainty. The power producer need to estimate this more accurately, but error happens anyway. So sometimes, even though he's pretty good enough, but he cannot get into the market. And there is an uncertainty. And the uncertainty increases the price, actually. So from optimization perspective, it would be better that everybody gets paid using the single price, market price. And that price is determined by the system operator in the spot market as well as in day ahead market. Okay. So, yeah, this is the price when it is selected, and the 35 is the marginal cost of the most expensive generator. Okay. Period 2, load 750. You can do the similar things, and this is the final result. Generator 1, 500, generator 2, 250. And then this is more expensive generator than that one, so marginal cost is $30. So S&P is 30. Time period 3, load is 1050 megawatt. So all the generators need to be turned on. And then, this is the most inefficient generator. So again, the S&P is $35. Okay. So in this simple example, for simplicity, we didn't consider turn on startup cost. Okay. Okay, any questions so far? And what is missing here? One thing is missing here. What is that? You are a power producer. There are three power producers. Yeah, 1, 2, 3. Do you think they are happy about this result? What is missing? The price is just determined from the marginal cost. And we determine the schedule that minimizes the total cost, right? Then how they can recover their fixed cost? We need to have some mechanism to recover their fixed cost, not just marginal cost. Okay? You see what I'm saying? Okay. When you look at this, now it will be clear what I'm saying. Period 1, 2, 3, time, slots. And this is the price, 35, 30, 35. And we have 3 units, 1, 2, 3. And each unit has its output. And they have their marginal cost and the fixed cost. So revenue can be computed. So there is a price and the amount of generation. So this times that is the revenue. Not working, this times that is the revenue. And there is a cost. This cost comes from marginal cost and fixed cost. Okay, so fixed cost plus marginal cost times the amount of generation gives this cost. And then the profit is revenue minus cost. Minus. Time period 2 minus. Time period 3 minus. So unit 1 is lucky because its fixed cost may not be that much. No, it's huge, but anyway, it can get some profit. But unit 2 and unit 3, actually, unit 2, no, the profit is negative. Unit 3, negative, 0 negatives. So they don't have any incentive to participate in this market. So the payment must be adjusted slightly to recover the fixed cost. Is this clear? 예지. Not clear. You look puzzled. So please check it later. So because there is a fixed cost, there is a mechanism which is called uplift payment. Uplift payment means just a compensation, payment compensation. Okay, uplift is uplift. And this is one possible formula of uplift payment. And in your textbook, there are 3 different types of uplift payment, but I just want to talk about this one. So this pi t star, this is S&P that is determined before. And this is the, what is KT? This is the total payment, the sum of total payment to all generators at time slot t. Okay, so the total payment comes from the S&P times the total load plus some adjustment. Okay, and this some adjustment is, what is it? So this symbol is not introduced before, but this eta I is the this kind of thing. The how can I say? What is the name of that? The loss participating in the market because of the fixed cost. Okay, so we need to compensate that. And anyway, this is a positive number. Okay, so some of those things. So what it want to do is to make sure that at least when they participate in the market, their profit should be greater than or equal to 0. Okay, so for all the units, this is the sum of the deficit of each generator. Okay, so we want to compensate this amount of money, and that is divided by the total load. The time horizon is 3, so total load. So this is the dollar per megawatt, dollar per megawatt hour. This is the this is the loss measured in dollar per megawatt hour. So we want to pay more, and that times the total load. So you can think this is dollar per megawatt hour of compensation. This is money. This is a megawatt hour. So this is the compensation price. So, and this is just lambda LT. So pi t star plus this one. So this is the quantity of compensation, dollar per megawatt hour. Okay, so in this example, we have 3 times loss. The total energy payment from S&P is blah, and this uplift payment is blah, and then unit 2 and unit 3 would be happier than before. Okay, this is not the only one, and there are other options, but I don't want to talk about that. So anyway, there is a mechanism to compensate the fixed cost using this uplift payment scheme.
앞에 봤던 티어리드 1, 2, 3에서 그 마켓 클리어링 프라이스를 정한 것들이 어떻게 보면은 마지널 커스트가 제일 높은 유닛들의 그 달러로 마켓 클리어링 프라이스를 정한 거잖아요. 근데 그래서 그것도 저 프로핏의 마이너스 요인으로 적용할 수도 있지 않나요? 근데
No. Pi t star comes from the highest marginal cost, right? So that is good for everyone. It's better for the cheaper generator, but anyway, from marginal cost perspective, everybody is happy, right? But there is a fixed cost, and then to compensate the fixed cost, another types of payment is possible. 네.
픽스드 코스트를 고려해서 보상을 해주려고 엄리프트 페이먼트를 하는 건데 에타에 대해서 혹시 한 번만 더 알려주시겠습니까?
Yeah, this eta is this kind of loss. I would call it loss because they participate in the market to earn money, but no, actually there is a loss. The profit is negative. So the absolute value of negative profit and sum of that is the amount of we need to compensate.
에타가 그러면 양수인 건가요?
Yes.
근데 여기서 에타는 꼭 저 손실이 얼만큼만 정확하게 결국에 정해지는 건 아니고 그냥
Yeah, keep talking.
그러니까 저 손실로부터 딱 정확하게 한 가지 값으로 계산되는 건 아니에요. 그러니까 그 저 손실을 그 0으로 만들도록 해야 되는 건지 아니면은 0보다 크게 해도 되는 건지.
Let's see. 100. So here in this example, the sum of this is 450, and the total load is the sum of this one, and compute it. So check it whether that is same to this one. Okay. But what I want to say here is that this is just one method. Okay, and we can have another method as well. So the uplift payment option 2 is something like this. When this SMP is determined, using that price, and the delivered power, there is a profit, and then assuming this price, each generator can adjust their power output, either turn on, adjust their output generation to maximize the difference. So if I'm allowed to change my generation, then how much that difference would be. And using that, uplift payment can be determined. Anyway, so there are many different types of payment scheme, uplift payment scheme. Okay. Good. So before going to the spot market, manage the spot market, I want to compare the centralized trading and bilateral trading. So centralized trading is economically unusual because this is administered centrally. So from economist perspective, transactions is bilateral. It would not require a centralized governor. Okay? So this is more like a system engineer perspective, right? So they have scheduling, SMP, this comes from optimization perspective, not market mechanism. So economically economically unusual because it should be administered centrally, and the price is not transparent. Bilateral trading, when they agree to each other, the price is determined. Here, optimization, cost, the fixed cost, compensate, complicated optimization problem, unit commitment, and facilitates security function. The privacy is important, and so makes possible central optimization. And historically, it origins in electricity industry, mostly in the United States. The exception is Pacific Northwest. But similar thing can happen using bilateral. And this is more economically feasible. And then the price is just set by two parties, and hard bargaining is possible. Of course, generators assume scheduling risk and must be coordinated with security function also to ensure privacy and security. And these are preferred in Europe. Okay. Don't ask me why. Europe and North America are different history. Anyway, both forms of trading can coexist. And let's go to the spot market. Actually, the managed spot market. Spot market is general. No. Spot market for wheat, flour, oil, gas, blah blah. But for electricity, it is called managed spot market because we have a system operator. So, in this managed spot market, by the way, so now the forward contract, day ahead scheduling, and actually gate closes, and now we are at the spot market. Okay, so the spot market is required to balance the power system. Any mismatch that was made in day ahead scheduling or in the forward market can be compensated in the spot market. You see what I'm saying? So no scheduling is required in spot market. That means no reservation. When you go to Kogujang, we don't need to make a reservation. There are a lot of seats, right? So the information required is bids to increase production or bids to decrease production or bids to decrease load, bids to increase load. So all of these bids for generation or load is required to balancing. And the generation surplus, generation deficit, load surplus, load deficit. And using this information, the action is determined. And the spot price is also determined. And the spot price is very volatile. Okay? And actually in Korea, we do not have real-time market. Okay? In Korea, we do not have real-time market, but no, in other countries, no, there exists real-time market. And the spot price is really like a noise. Sometimes it spikes up and down, spikes up. But the volume is very small, usually, when the price spikes up. The one who can provide the power is limited, so the volume is small. Anyway, so this comes from the control perspective. And in your textbook, there is another figure like this. So system operator manages spot market, and the contractual position of the producer and consumer offer to increase production or decrease demand, or bids to increase demand or decrease generation. Yeah, and very short-term load forecasting. The very short term means like 5 minutes, 50 minutes, less than 1 hour. Okay. So, as I told you, this is called managed spot market, and it is to balance load and generation. It is run by system operator, ISO, KPX, for example. Yeah, but in Korea, this is not a market. Okay, just KPX balances the power system, but other country there is a spot market run by system operator. So it maintains the operational reliability of the system, and it must operate on a sound economic basis. So use competitive bids for generation adjustment and determine a cost reflective spot price. So even though it is physically related with the system, still there is a concept of bid and offer. Okay, and the system operator can choose which bid and offer to select. Okay. So, but this is not a true market because the price is not set through interaction of buyers and sellers. Maybe you are confused. So there is bid from buyers and sellers, and also the producers can submit 2 types of different bids, increase or decrease of their generation, because imbalance can happen. Imbalance can be compensated by increasing the power generation or decreasing the power generation. And generator can have two positions, right? You may want to increase or decrease if I give you some money. You see what I'm saying? You don't know what I'm saying. We will see. We will see one example. Okay. So what I'm trying to say is, okay, we assume a spot market. I assume the spot market has infinite capacity. So any kind of imbalance can compensate in this spot market. This is my assumption. But to make that assumption viable, at least the total volume traded in the spot market should be minimized. That's why we have forward market, future market, day ahead scheduling. So slight imbalance can be resolved in the spot market, and we assume that spot market has that kind of enough capacity. Okay. So, by the way, so before entering into spot market, there is a concept called gate closure. So in the forward market, day ahead market, and then we have real-time market or spot market. But there is a time when no further transaction is allowed. That is called gate closure. Yeah, gate closes, and hey, no transaction between you guys. After this point, I'm the one who manages all the things. Okay, that's the system operator says. So there is a lead time, like June 11th, 2 p.m. And using some lead time, there is a gate closure, right? Then the question is, how much should this lead time? From system operators' perspective, they want to have it sufficiently large so that they have enough time to adjust things. But from market participants' perspective, seller or buyer, they want to make it shorter because if this gap is big, then there is another type of uncertainty, right? So yeah, two parties, the system operators and market participants, have different perspective about this gap, lead time. Okay, so read the textbook about this topic. And so now we are in the spot market. So yeah, spot market. Bolduria Power's position again. Suppose that this is scheduled before. Last lecture, it was determined. Okay, in the forward market, right? Scheduled power generation. But now we are in the spot market, and the Bolduria Power has 3 units with minimum and maximum and some marginal cost. Then in the spot market, they can bid. So here the bid and offer use slightly different meaning from the previous slide. So, and they are used in other way, so it is slightly confusing. And so it would be better to use bid only. And anyway, so this is a bidding. So increase bidding. So Bolduria's power spot market bids are like this. Unit C, this is very expensive one. And actually it is not scheduled, it is scheduled nothing. The maximum power is 50. This is a very expensive one. So he bids this amount using this price. Yeah, this is slightly different from this marginal cost. It is not necessarily same to the marginal cost. Anyway, this is the bid, price and quantity. Okay, so as long as it makes profit, then that is okay to Bolduria Power. Okay, so the increase bid, and this is a decrease offer. A and B. What it says is, okay, yeah, so this is, I can reduce 30 megawatt and the price is this much. That means actually and yeah, so this is the price it needs to pay, not get. Why? So originally, unit B is scheduled to provide 80 megawatt. Okay, but his offer is like that. I can reduce up to 30 megawatt, and that means I cannot fulfill my requirement. But if the penalty is this much, then I would prefer this one. The reason is because the marginal cost is $13. If the penalty is just 12.5, this would be better. Rather than generating power, just pay some money and generate nothing, right? So this is that. And for unit A, wow, this is the minimum. Yeah, so anyway, when these generators are turned on, this is the minimum generation. So the maximum amount to reduce is 30 this case and 400 that case. I'm willing to do that if the penalty is less than my marginal cost. Okay, then the Bolduria Power thinks it would be better to pay this penalty rather than using some gas and operating the power generator. It anyway cost me that much, that is higher than this one. Okay, so this is just bid. The system operator can or may or may not accept this bid, and they accept the bids if that is useful to balance the system. Okay, so all of this kind of complicated procedure is to balance the system. So in this managed spot market, produce more or consume less. This is a producer's perspective, this is a consumer's perspective. They receive spot price. Similarly, produce less or consume more. So produce less means I produce less than I was about to do. Then pay the spot price because I cannot fulfill my requirement. Okay. More generation, receive spot price. Less generation, pay the spot price. Same spot price can be used for either incentive or penalty. So yeah, we are here. And decentralized trading and bilateral trading, this is just general one. Okay, so now let's see. Now we are on the spot. Now it's time, June 11th, 2 p.m. Finally, the time has come. And it is determined that spot price is very expensive, $18.25. Okay, and then things happen, and unit B of Bolduria Power could produce only 10 megawatt hour instead of 80 megawatt hour. Something bad happened. Okay, so So that means Bolivia Power has a deficit of 70 megawatt hour for this hour. Okay, this kind of thing can happen. You see what's going on. And by the way, this is the bid of Bolivia Power. $40 megawatt of spot market bid. Sorry, so 50 megawatt at this price. What is that? Yeah, this one. So this is the maximum amount, and this is the price of bid. And yeah, the problem happened to here. But using unit C, Bolivia Power, this is another bid. Okay, so they can, 70 megawatt is in deficit from unit B, but unit C can provide up to 50 megawatt. Okay, and the system operator knows that. So the 40 megawatt of Bolivia Power spot market bid out of 50 megawatt at this price was called by the operator. The called means it is accepted by the operator. And then you may think, hey, what about then 30 megawatt? Anyway, the difference, 70 megawatt of deficit, 40 megawatt of that can be compensated here. Anywhere, somebody can provide 30 megawatt. So the balance is achieved. And because of that, this spot price is determined anyway. Okay? So finally, this is the end after, this is the result after 3 p.m. So, this is all the ones we went through. Cheapo energy, Bolivia steel, quality electro, blah blah blah, using forward, future, and forward contracts. Remember that. Selling and buying again, so 570, right? So the price and income were expensive. And the power exchange, you remember, in before noon, grabbed 3 bids, but after that got a phone call, right? So cannot provide 50 megawatt. So grab another offer, that is this one. So need to buy, so that is an expense and generation, and this is the income. And in the spot market, 2 things happened. Imbalance because of the failure of unit B, 70 megawatt. So he cannot fulfill his requirement, and this is the spot price. So this is the expense. But using unit C, in the spot market, the 40 megawatt was called using the spot price, even though the bid was 17.5. Where is it? Yeah, 17.5, but no, S&P is this one. So he gets paid 14 times 17.25 this income. Okay, so totally, this is the total amount of generation, 550 from 2 p.m. to 3 p.m. And this is the total income and total expense. So from system operator's perspective, there are different types of contracts. For the contract, future contract, unit A, B, C, blah, blah, blah. But anyway, this number is important. But different income and different expense. The interesting thing here is that, the unit B, I don't know where is it. Anyway, so yeah, this is in the textbook. Yeah, same information. Instead of this one, this is what we used before. But the production cost using unit A, B, C. Each generator produce 510 and 40, and we put minus so that sum of this should be 0. Okay. So anyway, the result is unit A generates 500, unit B generate 10, unit C generate 40. Okay. That's it. So if you are unsure what we discussed so far, as long as you understand this last slide, then you are okay. That means you understand the concept of future market, of forward market, the spot market, and adjustment. On June 11th, before noon, after noon, 2 p.m. Blah. Any questions? Okay, so this is the end of chapter 3. I will give you some homework problems so then you can study. And next Monday, as we already talked about, we will go to Dangani power plant. Yeah, and we'll have lunch together. If there is enough table for us. Yeah, so I called Monto Bene and they said, yeah, for 12 people, then you must eat at least more than 100 man won. So what? What? Why is it? Then she said, yeah, because blah, blah, blah. Okay, okay. So maybe we need to find another restaurant. Okay, thank you.